Well, we've had a look at resistors in parallel. We're going to have a look at capacitors in parallel. We have an example of two capacitors in parallel, one with 10 microfarad, one with 100. Then we've got an example of three capacitors in parallel, again a 10, 100 and then another 100 attached. You can see here that the formula for calculating total capacitance is the same as series resistance. So it's just total capacitance equals C1 plus C2, and again if you've got three in parallel it's C1 plus C2 plus C3 and so forth. So just using the two capacitors in parallel as an example, you can see here that we've got one capacitor here, we've got another capacitor here. But what's happening when you put these in parallel, you're effectively increasing plate, as you can see here. So the dielectric, the red part, is not what's increasing, it's actually the surface area across the capacitor, or the plate area if you want to look at it like that. And if you look at the formula for actually calculating right capacitance, you can see here capacitance is equal to a constant, right, which is 8.85 times 10 to the negative 12, your relative permeability, of the dielectric, and that's this part of the formula here. And then you've got the area in square meters, represented by A, and then you've got the distance between the plates represented by D. But the only part we're actually changing of all this is the area. So you can see here if the area increases, the capacitance must increase. Basically what it's saying is that as you keep adding capacitors in parallel, you're effectively increasing the plate area. And if you're increasing the plate area, then you're increasing the actual capacitance itself, and you can see that as I pointed out before by the formula itself. We're not increasing D, which is the distance between the plates, we're increasing the area of the plate overall. So what we've got here is three capacitors. So you can see we've got 10 microfarad, we've got 100 microfarad and another 100 microfarad. There is quite a large tolerances with these capacitors. I think it's plus or minus 10%, for these ones. And these are electrolytic, which means they're polarized, so you have a positive side and a negative side of the capacitor itself. So what we'll do is we'll measure each one, we'll write that down, and then we'll see if they add up as we're specified. So what we're measuring here is the 10 microfarad capacitor, and you can see it measures as 8.3 microfarad. So we'll just call it 8.3. So we've got one of the 100 microfarad capacitors. You can see that that's reading 82.07, so we'll call it 82.1 microfarad. And here we've got the other 100 microfarad capacitor. You can see we're getting a reading of 80.72 microfarad, so we'll call it 80.7. So what I've done here is just attach the three capacitors you can see there, 100, 100 and then a 10. I've got the negative side of these capacitors to one side and the positive side goes to the other side because they're polarized, and they're in parallel with each other. So we can now attach our probes to here and get an overall reading, and we'll see what happens there. So as you can see, I've attached the probes. Our reading is 170 microfarad. Well, there's C1, that's the 10 microfarad. So we've measured 8.3, C2 was 82.1, and C3 was 80.7 approximately. You can see we added up to 171.1 microfarad, and the reading that we got was just a bit over 170 microfarad. So we're pretty much in the ballpark, and you can see that these are adding up to the figure, and that kind of proves that putting capacitors in parallel, you work out the total capacitance by just adding the capacitors together, like we've done here or here, and you'll end up with your value. But just keep in mind with capacitors, they do vary quite a bit with reference to what's stamped on the capacitor or marked on the capacitor. as to an actual capacitance reading of that particular capacitor. So just be aware of that.